Welcome to our lesson over direct and inverse variation. Today, we have a pretty no-nonsense lesson. We're going to be going through some straightforward example problems, and then you'll be answering 10 questions of your own. Well, one is a bonus. I do recommend that if you are somebody that struggles with maybe solving equations, even just a basic equation, go ahead and bring up Desmos to guide you. I'm not going to be toggling between Desmos and doing the work by hand, but you obviously are able to use Desmos at any point that you need. Let's get started with direct variation. What is direct variation? It's simply a relationship between x and y that's very direct. It follows the equation y equals kx. Now, that really looks just like a line, and it is a line. You know, instead of using m in front of the x to represent slope, we use k. And that's just called the constant of variation. Don't ask me why we have to make things more complicated, but look at what this really is. This is y equals mx plus b, right? And our m and our k are the same thing here. I'll go ahead and make those red. So k is the same thing as m. It's just like our slope or our relationship between x and y. And then what's our b in direct variation? Do we have a plus anything here? Our b is 0. So that means direct variation graphs are just straight lines that pass through the origin. B is 0, that means our y-intercept is 0. So anytime you see a line, all lines are straight, anytime you see a line that's oblique, so it can't be vertical or horizontal, it's oblique, meaning it's diagonal, a positive or a negative slope. If you see a line passing through the origin, that means it's direct variation, or it represents x and y values that are directly varied. So let's see, which one of these graphs represents direct variation? A doesn't. It's an oblique line, but it doesn't pass through the origin. B is an oblique line, and it passes through the origin. C is not an oblique line. It's a vertical line. Plus, it doesn't even pass through the origin, so 2 strikes. You're out. And D is not a line. So D is definitely not direct variation. Okay, go ahead and try this one. Let's get a little bit more into the algebraic definition of direct variation. The way that we actually write this out and the way that you'll be reading it is that y varies directly as x. When you see y varies directly as x, you know that you immediately need to write down y equals kx. That is the equation for direct variation that you're going to be using. K is called the constant of variation. It's essentially the slope of the line. So how can we figure out whether or not x and y values, say if we're given them in a table, represent direct variation? The way that we can figure that out is if there's a consistent pattern between each x to its y, so between each x and its corresponding y. You either multiply or divide by the same number to get from x to y. Whatever that number is, that's k, our constant of variation. Now, technically, dividing by a number, we could say to go from x to y, we might multiply by 2 or we might divide by 2. Saying dividing by 2 really means multiplying by a half. So essentially, we're multiplying by either some integer value or some larger value, or we're multiplying x by a fraction each time to get to y. Let's actually look at this instead of keep talking about it. Here's an example. We have data in a table. We want to know, this is an example of direct variation. So we're told y varies directly as x here. This definitely follows the form y equals kx. And we want to essentially know what that k is. So direct variation has this equation. How are we getting from each x to y? What's the pattern there? We're multiplying by 2. I'm just going to write it once, but we do it every single time. It's consistent. So that means the equation is y equals 2x. If we plugged in, let's say 6 for x here, we'd have y equals 2 times 6. Y equals 12. That works for any y value now on this direct variation function here. What is the constant of variation? 2. Here's another example of direct variation. So we can see going from x to y, we want to establish that pattern. How are we getting from each x to y? What are we doing? Well, it looks like we're dividing by 3, but we don't really want to write dividing by 3. We can write multiplying by 1/3. That's essentially what that means. So the constant of variation is 1/3. Now that means our equation, our direct variation equation, because equations for direct variation are y equals kx, we can write this as y equals 1/3 x. I also want you to note that that x really can go in the numerator. And instead of y equals 1x over 3, we can simply write y equals x over 3. Please note that these are right here the equations. Well, the equation, just written in 2 different forms, representing these ordered pairs right here in the table. The constant of variation, k, is 1/3, because to get from each x to its corresponding y, we multiply by a third. 30 times a third is 10. 15 times a third is 5, and so on. Multiplying by a third is the same thing as dividing by 3. So if this is how you initially saw it, awesome. We want to make sure we get it to where it's what are we multiplying by. Now we're going to extend a little bit further, and we're going to ask ourselves to sort of make a prediction here. We've seen that a bit with our line of best fit, and maybe I wouldn't really call this a prediction. I would call this an exact, because this equation is exact. We're not estimating anything, but we're going to use our equation y equals 1/3 x. So we've established the equation, and we want to know what is y when x is -2. So we're asked to solve, use our equation to solve. Anytime we need to use our equation to solve, we need to make sure we already have our equation. So let's plug in what we need to plug in. X equals -2. So we're going to have y, because we're looking for y, equals 1/3 times x, which is -2. Now, if you're not a fraction person or don't want to do this by hand, just type this into Desmos. You don't need to type the y equals, just 1/3 times -2. Toggle it for a fraction or however your answer is written, and we'll see that we get y equals -2/3. Okay, another example, we want to know, is this direct variation? If yes, we want to give the constant of variation, which of course is k, and then the equation. So let's see, is there a pattern of, are we multiplying by the same thing to get from 4 to 6, 8 to 12, 12 to 18, and then 18 to 27? I don't know, because that's kind of weird to think about multiplying to get from 4 to 6. We'd actually have to multiply by 6/4. But if you don't see that there, if we're thinking 4 times what gives us 6, and we can really just do the opposite of division here. So we can do 6 over 4. We'll see that we get 1.5. And if you did that in Desmos, you'd get 1.5. Let's do 12 over 8. We can see that we'll get 1.5. And again, this is telling us that to get from 4 to 6, I multiplied by 1.5. I multiplied by 1.5. To get from 8 to 12, I multiplied by 1.5. To get from 12 to 18, we multiplied by 1.5. If you do 18 divided by 12, you can see that we'll again get 1.5. And then to get from 18 to 27, what did I multiply by? If I work backwards and do the division, we'll again see that we get 1.5. So all of these are times 1.5. There we go. So our constant of variation, K, is 1.5. So that was one where we had to use some division and work backwards because the numbers maybe weren't as easy. So that's our constant of variation. And our equation is y equals 1.5x because direct variation is y equals kx. Let's try another one. We want to know, is this direct variation? If yes, again, give the constant of variation k and the equation. So to get from 10 to 25, 6 to 15, 4 to 10, and 2 to 5. Let's see if we're multiplying by the same thing. So 25 over 10 is going to give us 2.5. So that means we multiplied by 2.5 to get from 10 to 25. Let's see if we did the same thing here. 15 over 6. We do also get 2.5. 10 over 4. We get 2.5. And 5 over 2. We also get 2.5. So we multiplied by the same thing each time, just gonna put little check marks there. So that means this does represent direct variation. I don't think I answered that last time, but yes, it does. Our K value is 2.5. And our equation, y equals kx, is y equals 2.5x. Okay, you're going to try one on your own that's very similar. Okay, now we're going to use direct variation to solve some problems and to find an unknown. So this is a pretty typical type of variation problem. We're given that y varies directly with x. So as soon as you see these words right here, what should you write down? Y equals kx. That's the first thing you want to do, is write that down. Step 1. Then we're given some information about it. Y equals 28 when x is 7. Let's plug those values in, and that's going to allow us to solve for our specific k value. So y equals 28. I don't know k, but k is being multiplied by x, which is 7. Now, normally in equations, we'd write that as 7k, but it doesn't really matter. Multiplication is commutative. We can write it either order. To solve for k, we're going to divide both sides by 7. So our k's will cancel, or rather our 7's cancel, and we get that k equals 28 divided by 7 is 4. So that means our k is 4. So now our third step is to rewrite and solve here. So we're going to have our equation, which is y equals kx, but we found that k is 4. So our equation is y equals 4x. We found k. Lastly, we're going to solve and answer the question. So our question is, we want to find x when y is 52. So I'm going to plug in 52 for y, and I need to find x. To find x, we're going to divide by 4. Again, if you want to use Desmos for this, feel free. You can type in 52 equals 4x, and it will give you your answer. But these problems are just one step and usually division. And we get 13, 52 divided by 4. Okay, let's do a similar one here. Y varies directly with x. That's what we're told. So the first step is to write down the proper equation. Y equals kx. Okay, the second step is to use the information that you're given to find k. So type that out. Use given x and y to find k. Okay, so we have y equals kx. So we'll have 6 equals K times 15. Okay, now to solve for K, we're going to divide both sides by 15. You can simplify this fraction for K using Desmos, put in 6 over 15 and hit that little circle button to the left. That'll give you your lowest fraction there, your simplest terms. Or I'm just going to divide, instead of writing 6 over 15, they're both divisible by 3. So we'll get 2 over 5. So we have that K is 2/5. Our equation then is y equals 2/5 x, because we found K is 2/5. Lastly, we're going to solve. So we want to find y this time when x is 2. So y equals 2/5 times 2. Again, if you plug that into Desmos, just do 2/5 times 2, and you can toggle it to be a fraction, and we'll get 4 over 5. Let's solve some word problems here. We have that miles vary, which should just say vary directly with gallons of gasoline. You get so many miles per gallon. A car uses 8 gallons of gasoline to travel 290 miles. How much gasoline will the car use to travel 400 miles? All right, we see very directly. So what do we want to write down? Y equals KX, very directly. Now, normally see Y varies directly as X. So in our case here, we're going to have its miles is Y, and gallons of gasoline is X, because its Y varies directly as X. So gasoline is going to be X, miles is going to be Y. I just want to establish that so when we see numbers, we know where to plug them in. So anytime we see gallons, it's X, and miles is going to be Y. Great. We're all set up and ready to go. Our next step is to use the given information. A car uses 8 gallons to travel 290 miles. All right, so let's plug that in to find K. What gets plugged in for Y? 8 or 290? Y is miles, so it's 290. And then 8 is gallons, so it's for X. Let's solve for K. We're going to divide both sides by 8. So we'll find that our K is, I'm using an old school calculator, we get 36.25. That's our slope here. That's our constant of variation, rather. That's how many miles per gallon we actually get. All right, so our equation is y equals 36.25x. Then lastly, how much gasoline will the car use? So how much gasoline? We're looking for gasoline. We're looking for X. When we travel 400 miles, miles is Y. So we'll plug in 400 for Y equals 36.25x. We're looking for X. So we're going to divide both sides by 36.25. I'm not going to show that step because I'm running out of room. So 400 divided by 36.25 is about 11 it's basically just 11 when we round. So 11 gallons. And gallons is GAL. G is grams. There we go. Okay, next up, that is our end of direct variation here. Next, we're going to talk about inverse variation. So inverse variation takes on 2 different equations. We can either talk about inverse variation as xy equals k. So x times y equals k. A little bit different. Or y equals k over x. We got there. If you take xy equals k and divided both sides by x, you have that y equals k over x. So these are simply the two ways that we can represent inverse variation as an equation. You're not going to be assessed on the graphs of inverse variation like you were for direct, but this is the general shape. It is a reciprocal function, y equals something over x, k over x, or a rational graph. And you will learn more about these types of graphs as you move further through your mathematics career. In order to figure out if a table of values represents inverse variation, it's easiest to think, does it follow this form? That's the easier of the two forms, xy equals k, rather than do a fraction, y equals k over x. So essentially, we want to know, when we multiply x times y, do we get a consistent value each time called k? Let's see. What's 2 times 12? That's 24. What's 3 times 8? That's 24. What's 4 times 6? 24. And what's 6 times 4? 24. So this table of values here represents inverse variation because they're all the same. So yes, the table represents inverse variation. If so, find the equation. Well, our k value is 24. So the equation can either be written as x, y equals 24, because that's one way. The other way to represent inverse variation besides this way is y equals k over x. So we could also write it as y equals 24 over x. That is our answer there. Let's try another one. Does this table represent inverse variation? So inverse variation, recall, is xy equals k or y equals k over x. That's inverse variation. We want to see, does it follow, does x times y equal a consistent k? So let's multiply our x times our y's each time. We'll get negative 12. So we need to keep getting negative 12. 3 times negative 4 is negative 12. 4 times negative 2 is negative 8. Nope. This does not represent inverse variation. Let's use inverse variation now to find our unknowns. So this is a very similar type of problem to what you've already seen. We're given that y varies inversely with x. You could also say that y is inversely proportional to x. So when we see that, you want to either write down xy equals k, or you can write down y equals k over x. It's really up to you which one you want to use. Whatever you're more comfortable plugging into and using. So I'll decide which one I want to use to go from here. So then we're given information again, and we're going to plug that information in to find k. Very similar here. Y equals 3 when x equals 21. So that's our next step. Y equals 3 when x equals 21. How would you rather plug this in? I'm going to go with my first one here. So I have x, 21, times y, 3. And that's going to equal my k value. So that means k equals 21 times 3, which is 63. So our equation, our direct variation, or our inverse variation equation rather, is x, y equals 63. Then lastly, I'm going to answer the question. Find y when x is 9. Find y when x is 9. All right, so find y when x is 9. So we'll have 9 times y equals 63. Divide both sides by 9, and we'll get that y equals 7. Y equals 7. And here is our last problem. We're going to use inverse variation to solve word problems. In order to do this, it's very similar, again, to the same thing we did for direct variation to solve a word problem. We want to make sure that we know what our variables represent. So we have the time it takes to do a job is inversely proportional, or varies inversely, to the number of workers. All right, I'm going to stop there. The time it takes to do a job. Time is measured in what in here? It looks like the time is measured in days. And then number of workers is just workers. So the time it takes, so we'd say y varies inversely as x. That's what I'm thinking. And so the y is our time. Time is measured in days. And x is our workers. So workers is x, days is y. So that's what we're working with here. Workers is x, days is y. Now we're going to use given information to solve for k. Oh, I got to write down my equation. My inverse variation equation is x, y equals k. That's what we're going to use here. All right, 8 workers can do the job in 6 days. So workers is x, y is days, and that'll allow us to find k. So I'm plugging in my given info here, second step to find k. We find that k is 48. Then I'm going to write out my equation because I found k. So my equation is xy equals 48. We are asked to solve 16 workers can do the same job in how many days? So I'm looking for y. I'm looking for how many days. Workers is 16. Workers is x equals 48. Divide both sides by 16. And we will have that y, how many days it takes, is 3 days. Nice job making it through this video. Go ahead and earn that last freebie point, and we'll see you soon.